Okay, hello. 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so hopefully these people show up. So yesterday evening, I meant to say it in lab and I did not. You guys have your outlines due this week on Thursday. I moved it to Thursday just because don't need to rush it really. I'll read them over spring break. Your outlines and then at least 5, you're welcome to have more than 5, primary literature sources that you're going to use for your presentation. And so I also put on presentation guidelines on Moodle. It's what I'm expecting from like that kind of final presentation. And the outline or paragraphy kind of thing, I leave that kind of open to you guys. I feel like you can put that together. I want to have a really good idea of what you're going to talk about, kind of like the logical order of what you're going to say, why you chose to talk about what you're going to talk about. Almost all of you had ideas. I've talked to a couple of you otherwise. Almost all of you had ideas that I thought would really work. But this is really like where you're going to be really explicit. You're not just going to say, this is what I want to do it on. You're going to say, here's what I'm going to say. And that shows me that you've not only looked for these papers, but you've probably looked into them a little bit. You've read them a little bit. You have an idea of what you're going to be able to tell us about. We're going to talk more about this, of course. But that outline is like a part of the grade for the presentation. Unlike the idea you gave me a couple weeks ago, this is actually something I like grade to see how it's looking. So again, should be pretty straightforward, pretty easy. Like I said, there's not like I don't have a determined format I'm looking for, but I want to see that you've thought about it and I can understand how we're going to talk, how you're going to have to talk to us for about 12 minutes about your topic. So you can email me if you want to, but those due Thursday by midnight on Thursday. So please, please, please get those in. All right, so this kind of like middle portion of the class, I know we're kind of now getting into the tail end of this middle portion. This is like where I really think we're talking about the most basic parts of animal biology. So sensing your environment, reproducing yourself, bringing in energy, food for you to eat, how anatomy is interacting with all those things. And then to this week, we're finally getting into locomotion. So you can have a really interesting debate as a biologist on what constitutes life. Is a virus really alive? It reproduces itself, but it can't reproduce itself without a host cell. That kind of an interesting conversation. And then once you get into living things, there's these big discrete groups. And one of those groups is animals, animalia. And even a long time ago, the first time people were starting to like put different kinds of living organisms into categories, animals were recognized different from plants, different from fungi. Back then, nobody knew about all the tiny stuff. Because animals have the ability, for the most part, to move. Throughout the life of an animal, there is locomotion. There's movement through your environment, active, searching for food, searching for mates, movement. There are, of course, many animals that do not move, but almost all of them move at some stage in their life cycle. So some of the ones that settle onto the bottom and don't seem to move anymore in the oceans, they have mobile juveniles after they hatch out of the egg. So today we're of course not talking about all animals, we're talking about vertebrates, but moving through your environment is something that is an animal thing. And of course, vertebrates do it quite well. We're going to start our locomotion talk in the water because that's where vertebrates evolved. So starting with swimming and locomoting within that kind of habitat. And then Frania, you're on Zoom, you can see everything, right?
Yep, I'm seeing.
Okay. So here's a really fun, totally boring like figure from like a chemistry or physics book. The density of these two mediums, the molecule number, a glass of air and a glass of water. Talk to your neighbors for a second. What are going to be the differences of locomoting, moving through air versus moving through water? We're going to talk to each other, please. All right, so what are some differences here? Some like high school science kind of stuff.
There's a lot less density.
There's a lot less dense, sure. So it's maybe easier to move through air than it is to move through water. in terms of the resistance you're gonna face from the medium. What's another thing?
The extra resistance from the water can also be a benefit because it's easier to push against the water.
Oh, okay, you can use the water, maybe easier than you can use the air. That's an interesting relationship to think about. Anything else? How about gravity? Gravity is present, of course, in both of these mediums, but there's different ways you can make yourself neutrally buoyant. The water's density allows you to actually be within it. I can choose to go like this in a pool. I cannot just do it here in this class, you're about to fall on the ground, right? So there's a buoyancy thing and there's the resistance thing. Of course, there's different densities. That's of course the big idea. How I think that plays out really interestingly is that certain animals utilize that difference between air and water in their locomotion. So a great example here is, of course, the force of that water coming over those falls. I mean, the water itself is more dense, but when it's coming over the falls like that, there's a lot of force in that water. So these salmon, when they have to cross a waterfall, they're going up into the air to get over, not just the force of that water, of course, but because the air is easier to travel through in this instance than the water is. And what's really cool is that there's a lot of different fishes, and we're gonna talk about some other animals too, a lot of different fishes that use that different density, even though they're very well adapted for being in the water, to their advantage sometimes. So this is a tuna. You can see maximum fin extension on this tuna, pectoral fins up in here. Here's the pelvic fins, anal fin as like a rudder. When a tuna is really chasing down prey and it's going really, really fast, it will stay near the surface and get like faster and faster because it'll go out into the air, which has less resistance. So once it gets to a certain speed, it can really like boost forward, kind of Mario Kart style as it's chasing fishes, which is a really interesting thing, really cool thing. So the other thing to talk about, of course, is buoyancy. We humans are mammals, so we have air in our lungs, but we're also adapted to be completely terrestrial. So when we go into the water, I don't know if any of you have scuba or anything like that, you have to take buoyancy into account. It's really difficult for a human just naturally to hold ourselves neutrally buoyant at depth. We're okay doing it at the surface. But of course, our lungs and the tank, but really it's our lungs, are full of air, and that's going to be positively buoyant. It's going to push you towards the surface. So we do things like we wear weight belts when we get in the water. So I don't know, has anybody scuba dived before? Yes, 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 yeah. So everybody has a certain amount of weight they wear. It's different for each person because all you're doing is counteracting your body weight, your lung capacity to keep you neutrally buoyant. So there's ways that we have to manufacture this in ourselves. And of course, you guys probably know several kinds of organisms have their own way of remaining neutrally buoyant. So probably the most derived one that it has it's like maybe the most impressive in terms of its like how it works is this thing you've now heard about a million different times, is that swim bladder that a lot of teleost actinopterygians have. So it is derived from the lung, or sorry, it is the same structure as the lung. It is derived from a kind of lung, not your lung, of course. And so some of these teleosts, they actively keep a certain amount of gas. They can take gas out of that chamber with their blood. They can put gas into that chamber with their blood to give themselves a neutral buoyancy. And so this is what happens to fishes. There are actinopterygian fishes, teleost fishes that we'll talk about after spring break that are like the deep, deep, deep sea organisms and live at these incredible pressures and the kind of regulation they do of their gas bladder to stay neutrally buoyant at the equivalent of like 60 atmospheres of pressure. So really interesting stuff to talk about there. You've heard about that before, this neutral buoyancy. Finally, we can talk about this. If you guys noticed it in lab last week. In lab last week, the chondrichthyans, right? The stingray, the shark, the ratfish, all of you were like, these livers are humongous. And so a lung structure branching off of a diverticulum in the foregut is an osteichthyan feature. So you have a lung and a coelacanth has a lung and a seahorse has a swim bladder, all from that same bony vertebrate, bony fish feature, that lung structure, used for buoyancy in many teleosts, used for breathing in some fishes, used for breathing in you. Here's another group of gnathostomes, the chondrichthyans. They do not have that. They never have. But sharks and rays are obviously incredibly successful in the water. And one of the ways they maintain their buoyancy is they have a gigantic liver. You guys have now at least, I guess, 60% of you have dissected at least out a giant chondrichthyan liver. And that liver is full of oils. You guys know oils are pretty buoyant.
They stay up on the surface, like when you're cooking and things like that. So these animals load up their liver with oils and they regulate the amount of oil in those livers, and that's how they achieve a neutral buoyancy. So a shark, as its fins out, it's always swimming forward. There's a lot of lift it generates with its fins, but there's a neutral buoyancy just inherent in its body in this gigantic liver. And that's one of the reasons sharks and rays have such tremendously huge livers. I was really biting my tongue last week in lab because I knew we were going to talk about buoyancy when we did locomotion. And so that is how they do it versus how a lot of Osteichthyans do it, which is really cool. A downside for some of these sharks that have these oil-filled livers is that oil-filled liver is an incredible source of meat and fat. It is a great thing to eat. There are all over the world, many, many, many times over. It just happened again, I think in South Africa, documented cases of orcas learning how to kill great white sharks, and all they want is the liver. So here's a great white shark that washed up on a beach, a bunch of orcas, so big killer whale, will chase it down. They usually beat it in the face a little bit, break its gills up. And then all they want is the liver. They eat that liver out of there. So this is a really awesome anatomical adaptation for buoyancy, but it's something that like once those smart whales figure out you have one, it's really a dangerous thing. So if you haven't, or if you are interested, I encourage you to Google it, great white shark orca, like it just happened where another pod learned how to do it. And so there's also some drone footage from like this January of like, it's the area off of South Africa where the great white sharks jump. And there's like none this year. So the tourism industry is all down because all these whales in the area learned how to do it. So you can see all the sharks like, because they're all marked, they just depart the area because they're gonna get got. Yeah.
I know there's also a pod in New Zealand that does the same thing.
Yeah.
And one of the ones, or rather two of the orcas being off the coast of Madagascar, I think, are named port and starboard. And
Because they attack from the sides.
well, no, because it's
That's who we're, yeah, right.
and they are very well known for just hunting mercilessly great white sharks.
So talking about locomotion, talking about the different kinds of ways animals get around. This is a very old school chart. I don't totally love all the pictures on it. I think some of them are a little outdated, but the general idea that I want to talk about is very clear in this image. So go ahead and talk to each other about this. Make some observations.
Like. And then they're one like the bike desert, like it also like inside. Yeah.
All right, so what are some observations we have on this chart?
There's a tree.
There's a tree. Yeah. Yep. Okay.
We were just kind of talking about like, we have land animals going through the water.
Yep.
And we're just comparing like sizes of.
Yes. What can you say?
Biggest size, like biggest animal on there is the water.
So these are all, this chart is supposed to represent kind of like, and again, it's a little outdated, but like some of the biggest versions of each of these different groups of animals. So all the biggest land animals are up there, the biggest land mammals, the biggest land animals of all time, which are dinosaurs, the biggest birds, the biggest things that fly. And then here's the biggest things in the water, the biggest shark, the biggest mammals in the water, biggest fish, the biggest squid. And I think a very solid observation you can take from this is The tree, of course, is a plant, but of all the animals, the things that have to move through their environments, the maximum size you can reach is hilariously more in water than it is on land. So the animals up on land, of course, have to walk around on limbs, on legs. They have to fly around. They're still up in the air. They're still facing gravity. The water, the oceans, it's neutrally buoyant. And so body size, both that elephant and that whale are mammals. That's the biggest current land mammal, the elephant. This big thing here is the fossil biggest mammal ever. And then of course, here's like a blue whale. And all I care about is that we let in the fact that truly humongous animals are going to be in the water almost certainly. That dinosaur, like I said, I don't love the drawing, but it's not doing such a bad job of showing you how big a lot of these big long dinosaurs could get. They can get a little bigger than that. Is still sort of like dealing with gravity, whereas that whale is cruising around in the water. So what I cared about here was just that general pattern of moving through water versus moving on land and how body size is going to be constrained by that. Thanks, Ronnie. Let's move forward. So I want to talk about some like things we haven't really done in this class before, which is like comparative and getting a little bit quantitative. So this is talking about how much it costs to move your body, and that's scaled to how big your body is. So to make these X and Y axis a little simpler for you, here's how much something weighs. So something like a hummingbird weighs less than a goose, weighs less than a helicopter. And then on this scale is how much it costs to move that thing relative to its weight, if that makes sense. So you can see there's a ton of data on here. There's different ways of moving through your environment. There's also things like what we do with our bodies, with our machines. There's a lot to unpack here. What are one or two really just basic observations we can make of these like totally verifiable relationships between size and moving and how you're moving and where you're moving? So go ahead and take a minute, take this all in, talk to each other. What are some very simple take homes we can make from this? Okay, go ahead. All right, okay, I'm gonna do another lap, whatever, but I want you guys, I'll prompt you a little bit. How would you describe the relationship between weight and cost for any one of these categories of movement? And how would you describe these categories relative to each other as locomotion? Okay, go ahead. All right, so for any one of these like locomotor types, so swimmers or walkers, what is the relationship between size and cost? Yeah, pick one. They all have the same, you guys think those, I think those lines are pretty close to parallel, so I think they all have pretty much the same relationship. What is the relationship?
As weight increases, the cost to move decreases.
Per unit weight, right? So yeah, these all are negative trending lines. So yes, those mosquitoes weigh the least of all the things on this chart, but their cost to move for their size is actually pretty high. This freaking freight train weighs a lot, but for what it is, its movement is really efficient. Does that make sense? That's what we're talking about here? A general increase in body mass. You're still heavier, it's still more energy in an absolute way, but the relative input of that energy, size is going to increase the efficiency of your movement. Does that make sense? Okay, so then tell me about the relationship between these different ways of locomoting. So it looks like the relationship holds true for most of these things. That's great. That's like a physical property we can all ascribe to. How are they related to each other?
They just have the lowest cost, and then flyers, and then like your walkers and runners.
So swimming can be thought of as like, for your size, the most efficient way of moving. It's more efficient. This fish weighs as much, or sorry, not weighs as much. It costs as much to move this fish as this move this horse, right? And this horse weighs quite a lot more. But the efficiency of that fish is way down. Well, no, they cost the same, right? Sorry, you can see. So yeah, they weigh completely differently, but the efficiency kind of is the same between them.
But I guess like the human does, it takes more prevention, so less like it maybe.
So we're gonna get into some swimming specifics here. You're totally right about that. One thing I really like about this is that this is a summary figure for all kinds of different kinds of locomoting. And I think it's interesting that people who do physics stuff always like want to include all the human machines, which I think is very interesting. But there's this line, the migratory line, which is about 20 joules for your amount of movement. I think the M is meters, I think, over kilogram. And it's what it is basically is like the cost of movement, and you have to be below that line for migration to be like something that makes sense to do. If you're too small, usually, or your locomotion is too inefficient, migration isn't going to be something that you can really do. And so there's a bunch of animals up there that don't migrate above that line, and a bunch of animals that maybe don't all migrate, but they have the ability to migrate below that line. And so this was just supposed to be something that shows the way that those different things interact with each other. So if we move into this is that same chart. I blocked out those text boxes because I think they're very distracting. This is specific to swimming. So this is all the data from that last slide, but just for the swimming organisms, fishes, underwater things that aren't fishes, and then things that swim on the surface. So go ahead and talk to each other about this. And it's the same, sorry, it's the same same scales, same axes. All right, what are some observations we can make about this?
What really surprised me is how like efficient humans are in the water, or like make things that live in the water, or at least to body weight.
Yeah, it is more efficient to their weight. I mean, that is the accurate way to read this chart. ducks, mink, and others. I don't know which one's the mink. This one. Those green, those like sort of other surface swimmers. But yeah, you're right. I mean, the human is like for its size, a little more efficient than some of those other surface swimmers. But that same pattern holds here, where if you take like an animal of this body weight, the fish is likely to be the most efficient. The thing that's maybe like the iguana or the turtles after that, and then things like ducks up on the surface are expending the most energy for something that is, you know, one set body size class. Again, you have your freight train in the water. The whale is absolutely the heaviest and actually is, for its size, the efficient mover. So blue whales are one of the most efficient animals on the planet in terms of like how much mass they move and how little energy it takes to move that mass. So again, same relationship with size, taking shape, and then that same idea that we saw, I think of it as this. So this one is like, for a given weight, you weigh this much. A swimmer is more efficient than a flyer, more efficient than a walker. I messed that up a second ago, but that's what it was, right? If you weigh 1 kilogram, cost of movement, swimming, and you have to be adapted to do these things, right? It's not just like choosing to do one or the other. Swimming, flying, walking. And then even within swimmers, the fishes, the vertebrates that swim on that trend line, that red trend line's a mess because there's like squid and shrimp and all kinds of stuff, sea lions on it. Non-fish swimmers, and then things that are on the surface. That same relationship holds with like these fishes, even within swimming, are the most adapted to their locomotion style. Yeah.
So we gotta talk about how like type of locomotion is important.
Oh, yeah.
Because within the water, even on the same trend line, like a whale obviously is very casually swimming, very
Yeah.
exploding through the water, whereas something like a shrimp is bursts
Totally.
of movement or squid bursts.
And completely different scales of how far they're traveling.
Yeah, so I think that the locomotion type is pretty important to how that works.
No, I think you're right about that. These graphs are always ones that make me a little bit uncomfortable because I'm always like, not all the points are labeled, right? Like which one's the mink? Anyway, there's that. You can look at that later. I want to talk about how animals move themselves. So here is our ancestral, not ancestral, but like our very much fish-focused vertebrate tree. I think you guys kind of know where you are on this tree. And something I like to point out is just how ancient the kind of locomoting that vertebrates do is, and how that locomotion is deeply, deeply, deeply inherited. So all of these animals that you see here move through the water. All of them do it. There's a lot of embellishment. There's a lot of fanciness, but all of them do it pretty much the same way. Even invertebrate chordates, like this amphioxus, the cephalochordate, they move in side-to-side locomotion. You guys know this. All of chordates have a notochord, a fibrous rod that has some flexibility to it, but it's pretty stiff. The ancestral thing that your vertebrae and all the vertebrae of these other animals ultimately descend from, that rod is rigid. And on either side of that rod, there's little sheets of muscles. They're shaped like a V on that amphioxus. And so on one side, the muscles flex and it bends the rod. And then the rod's natural elasticity pushes it back. The other side flexes, bending the rod on either side, moves you through the water. If you're this little ancient thing. Tunicate babies, another kind of invertebrate chordate, that's what they do. They flex on either side of the rod gets bent, the rod springs back, and they move through the water. So we call that lateral undulation. I know I'm describing it. You guys know what it looks like. Imagine in your brains any fish swimming. That's what I'm talking about. Moving the vertebrae and the tail, flexing, 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 side to side movement. That is the ancestral locomotion condition for vertebrata. Lateral undulation in the water. So obviously it gets fancier and fancier and fancier as we go through the vertebrate tree. Once we get up into like the true like gnathostomes, so not like hagfish and lamprey, there's a much more derived condition to those muscles that you see when you guys were cutting into fish last week. I know you all were cutting through these muscles. Any of you who eat fish are extremely familiar with this anatomy. These are these like sections called myomeres of muscle, and a myomere goes all the way up the body of the animal. There's a midline split where the lateral line is and a couple other features. That's a deep developmental thing. But you can see as we go up through vertebrate evolution, that like invertebrate chordate has basically like a V shape. A lot of the gnathostomes have what we call a W-shaped myomere, comes down a couple different times. And so that sheet of muscle all flexes at the same time against that central vertebral element. By the time we get to vertebrates, it's a true vertebral column, not a notochord. And so here's a tuna at a fish market cut open. This is how cut in half, really. This is what you guys were seeing in lab last week. What's this thing? That's the notochord, and then what's this? The body cavity, that's where all the guts were. Everything else in this tuna are those muscles. That's why we like to eat them, because they're made of food that we like. Their bodies are so full of meat. And so this like awesome, highly derived structure of muscles is why fishes are the most efficient swimmers in the oceans. They are incredibly, once you get up to whales, but incredibly well adapted. And this is like a very ancient structure of a rod in the middle and then fancier and fancier muscles and fins on the side. And so you guys kind of already know this. This is instinctually how fish move through the water. And so here's a diagram that always makes me like uncomfortable, talking about the physics of a wave of energy moving down a fish's body. So how pulsing along by flexing the muscles on either side of your notochord, your vertebral column, you're going to be generating thrust like a wave along your body. Different shapes of your fins, different shapes of the side of your body itself are going to make you a different kind of specialized swimmer in a different way. But either way, these waves of movement that you are initiating are pushing the water past you, pushing you forward through the water. And it's like a highly derived situation that has been specialized in so many ways. And so it's not just the body, it's not just the vertebral column and the muscles that are flexing. Of course, all fishes have different kinds of fins, and those fins are adapted in different ways. So plenty of fishes use their pectoral fins to do things like generate lift, which we'll talk about on Thursday when we talk about flying, where they're actually using their fin shape to like create a negative space above, so they're lifted in the water. They also can use thrust. We're going to see in a second here plenty of fishes that actually use their fins totally separate from how they use their vertebral column to move through the water. You can create propulsion in that way as well. Also, plenty of fishes that use their fins and the undulation of their spinal cord to move around on substrate. So they're not swimming at all. They're down on the bottom. But this whole idea of side-to-side movement based usually, and at least definitely ancestrally, on the vertebral column is how fishes move through the water. There's tons and tons of fancy accessories you can get. This is a yellowfin tuna, one of the fastest fishes in the water. There's lots of different shapes you can have to your tail. Some of these shapes, like this one up here, which is like a lungfish, are not at all about speed. They kind of are just there. Other ones like this tuna tail, you can see are very sharp, very severe, generate huge amounts of power when they're attached to this much muscle. I'm not going to get into what every single one of those different tail fins are, but the point is that this is one of those areas where evolution really tinkers, and these are almost all locomotion adaptations. The anal and dorsal fin, as well as these little finlets on a tuna, are all specific accessories of adaptation that really help it cut through the water in really efficient ways, breaking up the bow of water that's coming over the fish with these little turbulent breaking finlets on the base of its tail where all the power actually is happening. It's really cool to me that so many fish scales are so incredibly derived to give them like whatever their peak performance really is. So lots of anatomy in fish fin is going to be about those kind of accessories. I do want to talk just really briefly about some of like the best swimmers in the sea. So what do you guys notice about, if you didn't know it already, tuna meat?
Very red.
Dark red.
Very red. So why is it red? Lots of blood, there's lots of hemoglobin in there. These are extremely oxygenated muscle fibers. This animal is very metabolically intense, and it has to keep an incredible amount of blood flowing and oxygen flowing into its body because it puts so much effort into swimming. It has a very stiff, inflexible vertebral column that it rides those heavy muscles against to move it through the water so quickly. What I think is interesting is other pursuit predators in the oceans. And so this is a mako shark. And so you can see that lateral undulation. It looks a little bit silly when he's going that quickly. And so this is a speedboat with a bunch of like dead fish flapping behind it on lines. And so that's why the shark is chasing the boat, because it has the dead fish there. And so I think the lateral undulation is showing itself just fine. A lot of the propulsion is actually in the tail, although the shark is using its fins for lift. You guys know that sharks do not have bony skeletons. They have calcified cartilage, but still cartilage is relatively soft. That tuna has what is essentially like a broom handle of a vertebral column. It's like really hard to bend it, but it still does because its muscles are so heavy. And that's how it makes so much force. Super rigid vertebral column, just like the notochord of an invertebrate chordate. The shark has a like kind of smushier situation. I mean, it's not actually smushy, but it certainly doesn't have the same strength as bone. And something that only recently has been discovered is sharks, unlike the tuna, have those placoid scales all over their bodies. And there's specializations you can have that you can't see with your naked eye, but you can see under a microscope of those placoid scales. And sharks like mako sharks actually have such an intense interlocking of their scales that they're outside of their body. Their integument almost acts like that rigid internal notochord. It's so tough and resistant that they're flexing against almost their exoskeleton to generate really intense thrust. Also, those scales break up the water on like a very small level, way more efficiently than like any osteichthyon or actinopterygian does. So this is a rare example of a very fast chondrichthyon pursuit predator. And it's getting to be towards the speeds that tunas can get, but doing it with completely different anatomy, which I think is just like really spectacular. And also it's like, I never can decide if I think makos are scary or not. They're not huge, but like, I guess that's pretty intense. Chase on a boat. If you're a fish. So here's the other point I wanted to make about swimming, is I'm talking to you guys about lateral undulation, side to side movement, but there are tons and tons of other ways you can move through the watery world. So this is a very famous in comparative anatomy and really vertebrate biology figure from the mid 20th century, where we're on this x-axis here, we're talking about undulation, so how much of your body is moving through a wave of motion, versus oscillation. Some part of your body is moving like this. So undulation to oscillation. And then this is very inexact. There's kind of a scale here as we go from 12 up to 8 of what part of your body is producing the thrust to make you move through the water. So is it your trunk and your tail fin? Is it really just your tail fin? Is it any of your other fins? So it's not really a graph as much as it is a diagram showing you how different fish species, this eel versus that tuna versus that stingray or something up there, are using different kinds of fins to move through the water. I think it's easy just to show you guys GIFs. So here's how a ribbon eel really moves. So how much of the eel's body, what parts of the eel's body are actively being used in locomotion? It's like everything but its face, right? The entirety of an eel is undulating. The wave of movement that produces the thrust travels from basically its brain case to its tail. Tons of movement. Whereas if we look at something like a trunk fish, this is one of these relative to things like puffers. It's not a GIF, you'll see a GIF in a minute. That fish is encased in a box. Where's the meter? It is, all of this is completely solid. It's like a turtle almost. Only this part of it is even capable of moving. And so all it does is go with its tail and it moves through the water. Whereas the eel is using almost its entire body plan to create a wave of movement to move through the water. So undulation versus oscillation of movement. I want to show you a bunch of different fishes swimming in their own fun ways. I'll let you take it in one at a time. There's a knife fish swimming backwards with its anal fin. So it is not using its vertebral column. It is not using its mymeres, its muscles, the muscles of its body. It's creating a wave of movement on one of its fins. In this case, this is its anal fin to move through the water. Of course, you guys know this one. We've talked about this already. Stingrays and other batoids, they don't use their vertebral column almost at all to create any kind of thrust. They're swimming completely with their pectoral fins, which have evolved to be this huge disc that merges with the front of their face and goes all the way around to the back of their body and tucks in with their pelvic fins. So huge pectoral fin discs to create locomotion. You can compare that to this fish who's using just its tail to move through the water and a little bit of a movement on its vertebral column. One of my favorites, triggerfish, which are reef fishes. So you can imagine fishes that are in reef environments, which are complex shapes, lots of three-dimensional movement, not open water. They are really specialized in how they move around. So there's some movement of its pectoral fins there, but really it's its dorsal fin and its anal fin in tandem moving around to get it highly specifically moved through the environment. No real flexion of its vertebral column here, right? It can do that if it wants to. Probably the most extreme example of all this are something like a boxfish. So that kind of trunk fish I just showed you. Looks like a little UFO. As you watch it swim around a little bit. No flexion of its vertebral column, no flexion of its muscles at all. It's all the fins. So it's good to keep in mind that the fish default, the vertebrate ancestral condition is lateral undulation side to side. But in fishes, of course, there's tons and tons of ways to swim that do not actually involve moving your vertebral column around. Lots of specializations. Plenty of fishes that don't swim at all. So these are fully marine animals that live on the bottom of the ocean. You guys have seen most of these already. This was actually a slide you saw. There's plenty of underwater fishes that truly do walk around on their pectoral and pelvic fins. So actually go ahead and talk to them for a second. I've been blabbing. Enjoy these fishes. They all look sad? Maybe. This is called the red-lipped batfish. I hope you can tell why. Okay, sorry, see if you can figure out the pelvic and pectoral fins on all of these, like you can actually ID them. All right, where's the pectoral fins on that handfish, and where's the pelvic fins on the handfish? Okay. Where's the pelvic fins? These ones?
Yeah.
Okay, then where are the pectoral fins? These are the pectoral fins, and then in this fish, the pelvic fins are here. They've come up, they've come up, they've come up, they've come up all the way. So maybe a little more reasonable here. But pelvic fins and pectoral fins, these are fishes that are living in the water, but they're walking around. These four are all in a clade together. You saw them on a biodiversity slide earlier in class. Gurnards are related to things like tuna and seahorses and things like that. And they walk around on the bottom. This is their giant pectoral fin. It's like a wing. And in the very front, they have some lepidotrichia, some rays that they use to like mess with the dirt to get food to come out. And then of course I saved the best for last. Another member of the Gurnard, it's near the Gurnards in the family tree. It's not technically with them, but it's really close to them, are sea robins. I'll let you take it in on your own. That's a fish that's not using its vertebral column or really its fins. It's a locomote in the oceans. What's the sea robin doing? It does certainly seem to be walking, doesn't it? In a neutrally buoyant environment, it's in the water. And so those are actually also part of its pectoral fin girdle, but they're just loose fin rays that have flexibility. And so it does that. A lot of people find this gift unsettling. They have a very intense body plan. They have this big shovel face. They have these sensory barbules. They're really not like other fish. But that's why they're good, right? Exceptions to the rule. A lot of times in a class like this, it would be like, how do fishes move? They go like this. All right, now let's talk about otters. No. I want you guys to deal with all these fish.
It looks like the sea robin is using its caudal fin for forward thrust, and it's like walking so it doesn't run into the water.
Oh, absolutely. Every single one of these fishes too, if there's like actually a shark going, are gonna go to get a little movement, right? Doesn't mean they can't. And so you can see, yeah, there's a little, and that dorsal fin, look at the dorsal fin movement. So it's flapping. It's doing other things. It's just, I like this because all these examples of pectoral fin flapping or vertebral motion in different ways, I love these are just like, not at all. So these are fishes that are locomating in ways that are very different. And so here's that same kind of figure where we're talking about the different ways the body might move the wave through the water. So these all have different names. We're not going to worry about them. A strachiiform, this is an astrachiator. Tuniform, this is a tuna. Don't worry about the names. It's talking about how much of the body, how much of the fin is happening. And then what's interesting, of course, is that we can compare it across animals that are not related at all. Let's talk about their locomotor type. So carangiform is like the very back muscles and then into the tail. So a gator is in a carangiform locomotor in the water when it's in the water. And so it is interesting that, you know, biomechanics and locomotor specialists kind of try to come up with these different ways to talk about very different animals using very different anatomy move through the water. And so here's anguilliform. Anguilliforms, these are eels. So moving almost all the body, all the way back. There are plenty of aquatic tetrapods that move in these same ways. But I think it's interesting because even that is variable. So here's a newt. You can see how much of its body it's moving to get some swimming through the water. Firebelly newt is using most of its vertebral column, basically from its pectoral girdle backwards, to generate a wave to move through the water. Not as good as a fish, I think you'd agree. But of course, life is diverse. This table is giving you a misleading thing if you think all salamanders are like that. There's plenty of salamanders that are more like gators. They've got a good tail fin. The rough-skinned newt has a big, tall tail that has a broad surface. So it doesn't actually flex its vertebral column in its body, its thorax at all. It's doing it all in the tail. So even within some of these groups, where we can like throw them on a chart just for fun, there is locomotor biodiversity in getting around in the exact same kind of habitat. So there's of course plenty of things that swim that aren't just fishes. We call this oscillatory swimming when you're using, if you're a tetrapod, almost certainly, one of your limb sets to get your locomotion through the water. You guys know a lot of these animals already, and I think it's just really cool to actually take in the different ways this happens. So here's a bunch of animals that are not swimming in the water from a common ancestor. Even these two turtles come from a terrestrial ancestor that they share, even though they're both turtles. So go ahead and talk to each other about these 4 feet and how they're adapted for swimming.
Talking about evolution.
It's not too bad.
I've seen all the locomotion, like I know so much.
All right, so what are some things we're noticing? Webbing is pretty common, right? The turtle's got big claws. The beaver's got these claws, these nails, webbing between the fingers, but the webbing isn't always the same. The frog's got it all the way to the tips of its digits. The beaver absolutely doesn't. That sea turtle has no webbing at all. All of its bones are just encased in what is now truly a flipper. There is no more claw on the sea turtle. Of course, the birds do it even better. Here's a bunch of swimming birds. All of these birds have independently from each other evolved their aquatic habitats. They've all evolved to swim with their feet. Their common ancestor, every single common ancestor shared between all of these is not something that's swimming with its feet. So they've all done it their own way. Take a minute and make some observations. How are these birds using their feet differently to swim? They're all swimming on the surface of the water. Maybe they're diving sometimes. What actual details are shared? What details are actually different in all these swimming birds?
Some are breeds, very tiny.
All right, so tell me about bird feet. How are these birds all swimming with their feet?
Like paddles,
How, well, okay, be more specific.
like. I don't know, that's kind of what I got, like the beavers, they use their hind limbs to doggy paddle through the water.
All right, next. How are some differences between all these feet? I mean, Cass is of course correct. They're all using their feet to doggy paddle through the water. Yeah.
So like they have differential like uses for them in the water. Some are really deep diving type ducks where waterfowl get in and eat fish and things like that. But like a mallard duck, like a flat, I assume that's the kind
Yeah, I think it probably is, but I don't know.
of. They're a dabbling duck, so they're really only dunking their head and swimming a couple feet underwater kind of thing. They're not diving 50 feet.
So there's behavioral differences. I mean, all of these other ducks, though, you're right. Other ducks, though, that do dive are gonna have a foot that has this same architecture. So what about the different, I'm trying to get you guys, what about the different architecture of these feet? They are paddling, they are diving sometimes, they are on the surface sometimes. They're all capable of doing those things. Even the coot dives. How are these feet actually different from each other? Yes, they do.
Yeah, like full webbing and then. there's-
Full on webbing. The duck's got webbing all the way between its toes. Very tips of its toes got webbing. The cormorant, you can't really see it, but on the cormorant, that fourth toe that they all have. But even on the cormorant pelicans, there's webbing between that too. So there's three areas of webbing on a cormorant or a pelican, 2 areas of webbing on a duck. What's going on with the grebe's toes? Each individual toe has its own kind of like thing, its own flap, its own expansion. The coot, what's different about the coot then? Every phalanx, every bone has its own little whoop, whoop. And so when it closes its feet, it looks kind of like a normal bird foot, but when it goes to paddle, there's that much. So they're all increasing the surface area. Everything you guys said, of course, was right. They're all increasing the surface area, they're all oscillating their limbs, but there's completely different ways of doing that. And isn't that exactly what you'd expect if they're all sort of evolving to do this from ancestors that didn't? There's all kinds of ways to increase your foot surface area. I don't know if a coot in 40 million years will eventually have webbing or whatever, but it's really interesting that there's these different trade-offs. All of these animals are highly specialist, right? That's like a joke people make. A duck is invincible. It swims, it walks, it flies, it can do it all. So there's trade-offs here. This duck isn't going to become a whale anytime soon, and it's probably not going to become an albatross anytime soon. But it has this generalist body plan. It's really cool. All right, now I want to talk about these amniotes that are secondarily marine, that either are almost completely or are completely committed to living in the oceans. So here's a phylogeny that you guys definitely already know. None of these words should surprise you, but these are examples on the phylogeny, not of like general versions of mammals and birds and crocs and snakes, but marine adapted, ocean adapted amniotes, not even tetrapods, amniotes for the oceans. And so what you know about these animals, can you talk to each other? How do they swim through the water? How do they move their bodies? What anatomy do they use to swim with? These are amniotes, like full on laying an egg in the desert ancestor. Now they live in the oceans or go in the oceans all the time. How are they moving when they're in the water?
They bend their back.
All right, so how are these animals moving through the water? You could pick any one of them.
Snakes don't have flippers.
Snakes for sure don't have flippers. How's it moving through the water? Doing the snake thing, but in the water. Sea snakes actually do have an expansion dorsoventrally. Their body's compressed at the end of their body and their tails. They have a little bit of a fin. At least a flat shearing surface, sculpting surface to their posterior part of their body. All right, what about another one?
Whales,
What are whales doing?
dorsoventrally caudal, dorsoventral caudalation. I can't speak whatever.
They're using their vertebral column.
This was my moment to shine.
They're using, that was the big moment. They're using their caudal fins that they have re-evolved from nothing. So it's not at all homologous with like a fish's caudal fin, but it's still there. We don't call it that, right? We call it a fluke. They have a big fluke on their tail. And they go up and down. So it's still their vertebral column. Still a fin thing, but they evolved that from ancestors that were absolutely not doing that. Any other ones?
Penguin does have sort of fin, but like the snake, so instead of using its spine, it's all just using feet.
Penguin's using its wings. Interesting. Great question. So here's a snake moving through the water. It looks kind of like a normal snake, but it's got a little bit of an expansion on its tail, so it can swim pretty well. Here's a marine iguana moving through the water. I'll let you just observe these different things. I don't have a GIF. You'll see one later, but you know what this one's doing. A flock of birds, 60 feet down. This is like the whale. All right, so here's what I want you to think about for now, just to think about it. Here's the phylogeny with a penguin, and here's the phylogeny with a whale of its decently close relatives, of its bigger clade. The adaptation to living in the ocean is on that lineage only for the whale, and that lineage only for the penguin. And so how does everything around it locomote? What anatomy does everything around it use to locomote? Because that's going to inform the common ancestor of all of these different things, and then how that will utilize modified the anatomy it was inheriting to become a whale or become a penguin. Maybe talk to each other just for a quick second about this. You just saw the gifts. There you go. I'll let you look at that for another second. Okay, now talk about these questions.
Exactly. Before we go into everything, we find all of the specials, we find that we want to let whether while they're bending for a back. But it could be up there, like checking that, like they're all going to see. More like they want
How obviously the ancestors with.
I like it, it's slowly sounding like something like. About. A generic, love them, like.
All right, what are people, there's like 3 questions up here, so I'm not looking for you to answer any one of these. You can if you want to, but what are we talking about? Yeah,
I was talking about how if you look at all the land mammals, like that are tetrapods, when they're running, they're bending their back up and down in order to run on land. So the whale just sort of kept with that and just rolled with it.
okay, interesting observation. Does whale locomotion just represent a swimming version of like a running mammal? Amazing, interesting. What else are we talking about? I feel like you all kind of just had it instinctually, right? When you saw the GIF of all the penguins swimming underwater, you're like, oh, I've seen birds fly overhead. They're all just going like this. The penguin is a big fat torpedo though. It's not a bird like you usually expect at all. And its wings are relatively small. They're like very streamlined. They're very narrow in this dimension. But that is a bird that lives in the oceans, and all it does is fly underwater. Changed its density, changed its body shape. What we got, Frania? Thank you, Frania. All right, so now we're going to try to transition to land, because these are all land animals we were just talking about. So locomoting on land is very different than locomoting in the water. Obviously, big patterns are that body size is going to be more constrained by gravity. You have to have structural support for your body while you're moving. A whale, or even a better example is a jellyfish, can just go like Doesn't matter underwater. On land, on the beach, jellyfish doesn't do so good. So there's gravity to deal with. You have to support yourself. Moving on land, no matter what your body size, is relatively less efficient than moving on water. Okay. I can't get on the land without taking you back to the weirdo fishes. We always got to start with the fishes. Land fishes. So this is a shark, a chondrichthyon, a little epaulet shark. I'll let you make some observations about its locomotion in tide pools. That's the good one. That is not a baby, that's a grown adult. What's it doing? A what now? Crawling, how would you describe its movements?
It's moving like a person swims in water that's doing it.
A person swims in water?
You know, like, yeah, so like, it's like doing the doggy paddle, you know?
Doggy paddle, okay, okay, we're getting there, we're getting some good observations, looks like a doggy paddle.
So having a lot of spine movement side to side though.
Lateral undulation is happening, the body's going like this. What's it actually using to get a grip?
Using the lateral undulation to place its fins on the ground.
This is a shark using lateral undulation to put its pectoral and pelvic fins like in position. It's a walking shark. It's in tide pools, so it's in and out of the water, has to breathe underwater. It's still a shark that does that. Eels can get up on the land all the time and basically just be like snakes. They can cross between bodies of water. Catfishes can certainly get out of the water and walk. How's this catfish moving? Catfish on somebody's front porch in Florida. So always think about the direction of movement, vertebrae, not vertebrae, fins, not fins. How's the catfish doing it?
All like short bursts. So
Short burst of activity, sure. It's pretty stressful, probably. Here's a snakehead. This is a fish from like Asia, Southeast Asia, South Asia. How's this snakehead getting around? If there is a lot of sheer determination, the epaulet shark looks pretty chill, but everybody else looks uncomfortable. Lateral undulation, muscles against the vertebral column with some fins. The epaulet shark to me is hilarious because it is doing exactly what tetrapods do, where it's just going like this and walking with its pectoral fins and pelvic fins. There are some land crossing fishes that have even specialized adaptations. You can't see it, but there are barbs on the front of the pectoral fins of all catfishes, and that catfish is using those barbs to like get a grip. They point down when it's doing this to like grab the ground. This is my favorite example. A climbing perch, which is a kind of cichlid thing. What is it doing? What is it using? These are its pectoral fins. Pelvic fins are where you expect them to be. Maybe, they're right here. Can't see them in the gill. That's its a bony gill cover. It's got spikes on its gill cover. So this fish is completely unlike the others. It has its own adaptations. There's the spikes right there for crossing land. And all it does is it goes like, it's a very like horror movie kind of situation. But this is a fish that again can cross between fresh water. Maybe your pond's becoming anoxic, maybe your pond's got too many predators, maybe you're looking for a new place to breed, new food to eat. These are different fishes that have evolved ways to like switch which water they're in. The climbing perch on its own, it's the only one that does something like this, uses its operculum and has spikes on its operculum for locomoting on land. Kind of a nightmare, right?
how does it get around the dehydration that comes with exposing its gills?
I don't know the answer to that. I bet it's pretty brief. And it looks like it's wet on the ground. Maybe it just rained. This is a great behavioral question. I don't know the answer to this. There's, of course, a very famous example of fishes coming out onto land. These are a certain kind of teleosts called mud skippers. They are kind of goby. So Dr. Pradhan talked about gobies that change sex. Mud skippers don't do that, but mud skippers are probably like most land-friendly actinopterygian. These are all in South Asia and Australia. They climb out onto muddy banks and basically like live there. They fight. These are two males. We can talk, I could have showed you this for the reproduction part of class. These are males with their display structures. The display structures are not really for females, it's for each other to fight and intimidate. That one that's jumping is very clean. Those two are in the mud, having their fight. But look at how their eyeballs are placed. I mean, there's a bunch of anatomy with mud skippers, right? These are fishes that can see out of the water by staying almost all in the water, and they get up on the land there. So they fight each other, the males do, but they also display. That jumping picture is a very clean male doing his display. I'll show you, of course, them displaying for the females. So these are full-on teleosts that are comfortable out on the land. I mean, they're right next to the water, right? They don't go far, but they are on the land all the time. Lots of fin locomotion there. Also lots of body wall, vertebral column motivation there. Could not show you mud skippers if I was showing you all these nightmares. Okay. Side to side undulation we just talked about. Moving your muscles against your vertebral column is as a general rule, lateral undulation is the ancestral condition for all chordates, definitely for all vertebrates. It is what is inherited by all vertebrates. Then we work our way up the tree. We can add tetrapods. You guys are all comfortable with this at this point in the class, right? That I could just drop a rabbit and you're like, yep, I know that that's right. Okay, because it is. That's where the rabbit goes on this phylogeny. So let's get up into tetrapods. So here's tetrapods. Here's a bunch of amphibians and a bunch of amniotes. You guys know these animals. You know this phylogeny at this point pretty well. Lateral undulation is the ancestral condition for chordates, the ancestral condition for vertebrates, for gnathostomes, for osteichthyans, for sarcopterygians. Absolutely. Going up the tree with lateral undulation, we switch from tetrapods from being a tail-driven lateral undulation, where you have your fin, to being a limb-driven lateral undulation. You're still moving your vertebrae side to side, but limbs are what you are reaching out with. So this locomotory type is what's in the water. You saw a shark basically walking like this a second ago. Early tetrapods are also walking like this. Here's a good example. It's a reconstruction of one of the earliest tetrapods that we know from the fossil record. Canthostega, it's about almost 400 million year old early tetrapod, absolutely doing what that shark was doing, but it has little fingers on its pectoral and pelvic fins when it comes out of the water. Oh yeah, we're good. So the ancestral tetrapod locomotion is still lateral undulation, but instead of being tail driven, it is limb driven. So you can see the evolutionary trajectory of movement. So here's this newt swimming, but here's a salamander walking. See if you can convince yourself of its limb driven lateral undulation. Go ahead and compare and contrast these tetrapods walking.
Yeah.
All right, so any observations here?
They're all super wide stands.
All super wide stance, sprawling is the word people would use. There's different levels of being able to reach. There's a reason you guys have in your minds alligators and lizards being similar, salamanders being like lizards. This is like a lot of specializations. You guys know this already. Specializations in the skull and in the integument, in the reproductive, blah, blah, blah. But in terms of how they're locomoting, these completely different kinds of animals all are just showing you the ancestral tetrapod condition, walking like this on land. Your limbs can have a lot of reach, they can be stubby, but you're still moving your spine and moving your limbs together, lateral undulation to get your movement on land to happen. There's a reason you think of these things together and you don't put that one with turtles and birds in your head, right? Because it moves and looks a lot like a lizard, which moves and looks a lot like a salamander, and they all look and move like the ancestral land vertebrate does. It's really cool, the ancestral tetrapod. Plenty of lateral undulation with no limbs. So you guys know about snakes. Snakes, we're going to talk about their locomotion more on Thursday, but they certainly undulate their bodies. That's how they create forward movement. Here are 5 of the many other legless squamates. These are all different kinds of legless lizard. They all move their bodies, lateral undulation with no limbs. And then of course there's Sicilians, who are amphibians that have lateral undulation. That's how they move their bodies. All of these are slitherers. They slither around, but they're moving their bodies like this to do it. The difference, of course, for them is they've all independently lost their limbs. But when you see a snake do this in your yard, and you see a shark swimming in the ocean, that is like, you can imagine that same locomotory, super overarching pattern is there. So then, maybe the interesting thing to talk about is that many tetrapods are not driven by lateral undulation of their vertebral column and their limbs. So talk to each other for a second. Which of these animals are not being driven by lateral undulation of their column and their limbs?
Animals, birds. Well, yeah.
Right, so which one of these are not lateral undulation by limbs? They're doing something completely different than that. Birds, who else? Turtles, who else? And frogs. I know I just gave it away because I forgot if I had another question for you, but like, I hope that you can think of the Amphioxus, the hagfish, the coelacanth, the salamander, they're all going like this. And so then if you see the ones that are doing something different, you kind of already know there's a story there. There's adaptation there. There's an evolutionary heritage there that's worth checking out. Birds and turtles, frogs, and most, but not all mammals are doing something different. And so I know we have 2 minutes here. So we'll get into these just for a second. This is what we'll talk about on Thursday. So these different kinds of locomoting. So Anura is a monophyletic group that locomotes differently. Testudines is, Aves is, and Theria, so not all mammals, but Therian mammals are. So for the next minute, take the time, talk to your neighbors about the very different ways these 4 clades of tetrapods, are locomoting through their habitats. Okay, go ahead.
The member looking at the spine and their entire back is was a lot of the it's not like following the solid angle.
Which of these animals have the vertebral column involved in the locomotion? Other ones? The answer, of course, is that the birds, the frogs, the turtles have rigid backbones. And of course, that rigidity is part of their locomotion, but they're not undulating their bodies, right? That impala is undulating its vertebral column, but it's not going like this. It's going like this as it runs. But all right, that's what we'll kick off with on Thursday. And I will